In this section, we're going to talk about work. Now, the amount of work that needs to be done is always force times distance. Force times distance. In many cases, the force is just the weight of an object times the distance. Force is just the weight of the item. But weight sometimes is the volume times the density, which we denote by sigma. So volume times the density is weight times distance. Now let's talk about how density works and how it gives you weight. Suppose you have 30 cubic feet volume, and we multiply it by the density. The density is 20 pounds by 1 cubic foot. That's the density per unit volume. How dense is it? You can have 20 pounds per 1,000,000 miles. It's going to be very light for each little piece. But if you have 20 pounds in 1 cubic foot, it might be heavy to lift 1 cubic foot. Fine, it's only 20 pounds. But if you spread the 20 pounds, imagine you took a dumbbell, 20 pounds dumbbell, and you chopped it up into little pieces, little grains, and you put it on this little paper. That one little paper, so say it's 100 pounds, okay? That one little paper, it's going to be pretty heavy to lift, 100 pounds. But you know what? If you spread it over a lot of these pieces of paper, of course, it's not going to fall through the paper, okay? And the paper, we're going to neglect the weight of the paper. But now, if you spread out the grains of this cut up 100 pounds bar dumbbell, and you put equal amounts on each piece of paper, it's not very dense. If you put a number of them, if you put enough of them, and these boxes, believe it or not, they should all be the same size, okay? Especially the same size as that one. You put many of these. You just keep putting many of these. You can have a little baby lift up, say, that one, because it's not very dense. You took 100 pounds, but boy did you spread it out compared to spreading it out into 1 cubic foot area. Okay, so the bottom line is, if you have this condition, you have something that weighs 20 pounds per cubic feet, and you put it over 30 cubic feet, well, the cubic feet cancel out, and 30 times 20 is 600 pounds. Oh yeah, that looks like a weight to me. That's a weight. Okay, that is volume times density really does give you weight. So there was an example just to motivate that the units seem to be working out. So let's just change the lettering. Well, let's put letters. Instead of volumes, I'll put V. Instead of density, I'll put the density symbol, and instead of distance, I'll put D. That's what work is. Work is volume times density times distance, at least for the type of problems we're doing. For example, if I ask you to move a 500-pound couch 5 feet. I ask you to move a 500-pound couch 5 feet. Well, I would use work is equal to weight times distance formula. The weight is 500 pounds. The distance is 5 feet. 500 times 5 feet is 2,500. And foot times pound is a foot-pound. And if I remember my physics right, a foot-pound is called a slug. That is, the work that you did, fine, you never heard of the units before, but how many people talk about units of work anyways? In this case, you did 2,500 slugs of work, or 2,500 foot-pounds. I guess that should be an S, foot-pounds. So sometimes you use that. Other times, suppose you have a big block on the ground. Forget the frictional force between the floor and the box, and the box weighs, say, 500 pounds, and you are going to apply a force, and the force is going to be 10. You're going to apply a force. Well, the work is force times that's not going to work because I need to call force the weight. Okay, so let's just change that. You're going to apply a 500. The force is going to be 500, okay? And you were going to move it 10 feet. You were going to move it to here, where from here to here, that's 10 feet. So the answer is going to be 500 times 10 feet, and suppose your force is 500 pounds. Of course, this box is going to be crazy heavy for you to push it with 500 pounds. And it's going to be 5,000 foot-pounds. Okay, forget all that. For these type of work problems we're going to do, this is the formula. This here is the formula. And the first problem is going to be as follows. Let us say here's the ground, and you have this cylinder. Actually, let's make it bigger, and let's not call it a cylinder. Let's call it a barrel. So you have this big, gigantic barrel, and the barrel is full with water. It's full with water. And what you want to do is find out how much work it takes to pump the water out of the barrel. Not only that, the hose that the water is going to ultimately come out of is, say, 3 feet high. That distance is 3 feet. Okay? And the height of the cylinder is, say, 12 feet. And suppose that the radius is 8 feet. Big, gigantic barrel. 8 feet radius, that's 16 feet diameter, 12 feet high. And it's full with water. So now, what you want to do, and since I drew on it a little bit, I drew the 12 feet and 8 feet. Let's have a nice, clean picture of what's going on over here. And then you want to lift it up another 3 feet. Okay, this is 12 feet high and R is 8 feet. So let us look at the work that requires to move some arbitrary piece of water. Okay, and again, x-axis and y-axis down the middle. Well, the work is the volume, oops, that's not a V, nor is that the eraser. The work required is equal to, since it's continuous, we're going to be lifting up each and every slab. And the slabs are going to be very narrow, and those are delta y's. So the work is going to be the integral of the volume times the density times dy. In fact, delta W, the amount of work required to move this piece, is going to be delta V times the density times delta Y. Now, what is the volume? The volume is going to be pi times 8 squared, pi r squared. And I don't know if I said it was full with water, but I'm saying it now. It's full with water, and the density of water, if you're taking this course right now, you better know. It's 62.4. So the density is 62.4 times delta y. Okay, so we want to add up all these pieces. Now, we need to be careful what the delta y is. Well, something is bothering me here. I know what's bothering me here. The formula is volume times density times distance, V delta D. I failed to put in the D. Times D, and in our case, dy. So delta W is going to be the volume, which is pi times r squared, times the density, which is 62.4, times the distance, which we'll talk about in a moment. We have to figure out how high we're going to lift this, times delta y. Well, again, I guess I'll draw it. That there is the y-axis, where is positive up there. Now, how high do I have to lift this? If I'm starting at a height of y, if that height is y, how far do I need to lift it? Okay. Well, like I always say in my videos, so this is how high we want to lift it. This is how high we want to lift it. If you want to know a vertical height, it's the top height, vertical distance. It's the top minus the bottom. Well, the top way up here is, well, it's 12 feet plus another 3 feet. The top is 15 feet, and the height right here is y feet. So it's going to be 15 minus y. Okay, so the volume is going to be, the integral of, I meant to say the work, is going to equal the volume, which is pi times h squared, that's the volume, times the density, which is 62.4, times the distance that I raise the arbitrary piece times dy. Now, let us be sure that this is working correctly. The bottom piece, the bottom slab of water, forget about the water that's above it. Let's just consider that water. How far do I have to lift it? And the answer is, well, you have to lift it to a height of 15 from a height of 0. It better be 15. Well, if y starts at 0, y is going to go from 0 to 15. No, 0 to 12. Because the water level only goes from 0 to 12. Well, when y is 0, 15 minus 0, which is the distance, is 15. Bingo, that works perfectly because you have to lift that slab of water up 15 feet. Now, what if you're at the very top? What about the very top layer of water? That is when y is 12, because it's 12 feet. This is where y is 12. Well, 15 minus 12 is 3. Oh, this is looking good, because that top slab only has to go up that last 3 feet for the pipe. Okay, that at the bottom is the right formula, and we talked about why it's right. Why 15 minus y was correct. Alright. 64 times pi times that is going to be 64 times 62.4. I'll leave it to you to do that multiplication, times pi. So I dealt with that. All that survived is this. 15 minus y dy from 0 to 12. Now you can make a u substitution, but how about we just integrate it? So 64 times this number times pi. The integral of 15 is 15y minus y squared over 2. We go from 0 to 12. Plugging in 0 into this polynomial is going to give 0. So we don't have to worry about that. So we get 15 times 12 minus 12 times 12 over 2. Well, 2 goes into that 12 16 times. 6 times, excuse me. So now we are adding 12s. We have 15 12s here, and we are taking away 6 12s. We are going to have 9 12s. And I know what 9 12s is. It's 108. So if you multiply these 4 numbers times pi, 1, 2, 3, 4 numbers, that will be your answer. Okay, that is the work required to lift that water up to the 3 feet above the top. Okay. Now, how about we have a cone? We have this cone. And the height of the cone is 6 feet. The height of the cone is 6 feet, and the radius of the cone is 8 feet. 8 feet. And now we want to pump the water out. Okay, it's filled with water, and we want to pump it out. Okay, so here is the x-axis, here is the y-axis, and the hose is right at the top. The spigot that the water comes out of is right at the top. That is, we don't have to lift it any higher than the top. The water is just going to come out from here. If I can only draw this. Okay, the water is going to come out from there. And the question is, how much work is required? And the formula is, the work is the volume times the density times the distance, and since the slabs are delta y thickness, dy. And usually it's going to be dy because, well, you can label the axes any letter you want. But it's usually going to be vertically that the water is going to be pumped up to. Okay. So, let us look at this. And y is going to go from the lowest slab is at 0. And the top slab, again, is full with water. It could have been half full. The top is going to be 8. Going to go from 0 feet to 8 feet. So we have the integral from 0 to 8. The volume is pi times r squared. R again is 8. Times the density of water, which is 62.4, times the distance times dy. The distance is usually a little bit harder. We're starting at a height of y. How far do you have to lift it? Well, the top is 8, and this is y. It's top minus bottom. This 8 minus y. And we can make sure it's right. First, we start off when x is 0. 8 minus 0 is 8. So this little piece of drop of water down there, it has to go up 8 feet. If you're just a little bit higher than 0, 8 minus close to 0 is a little bit less than 8. Yeah, I'm going to have to lift this almost to 8 feet. At the very top, y is 8. Oh, look at this. 8 minus 8 is 0. That's exactly how far I have to lift this water. It's already at the top. Okay, so verify that. So now we have some constants. We have 8 squared times 62.4. That's 8 squared. That's 62.4 times pi. Times the integral from 0 to 8 of 8 minus y dy. Again, you can use substitution, but I'm not going to bother. It's no better, no worse. Integral of 8 is 8y minus the integral of y is y squared over 2 from 0 to 8. So we have this number. Don't grab out your calculator to find out what 8 times 8 is and what 8 times 8 over 2 is. But you know what? In this case, maybe it wasn't such a bad idea. But you really should know what 8 times 8 is. You have 1/64, and 8 times 8 over 2 is half for 64. Well, if you have one of these and you take away half of them, you're going to be left with half of 64, which is 32. So the answer, I'm going to put the 32 in the front. The answer is going to be 32 times that. 32 times 64 times 62.4 pi, and that's the answer. So that's the volume, sorry, that's the work required to move that water from all the water to pump it out. Okay, now, it doesn't matter if you pump out the top first and then what's below the top. I mean, you can calculate the work just pumping out the bottom, and then the work that's for the water right above it and right above it. But of course, when you're bringing up a slab of water from below, don't count the water above it, weighing it down or anything. Think about that. Okay. Now, let's do this problem. Suppose you have a hemisphere full with oil. And you also have the rest of the sphere. So believe it or not, that's a sphere. I'll try to draw it better. So you have a sphere, and that's the center, well, that's the equator. Okay, so now just this is filled with water. Okay, the bottom half is filled with oil. And I'm telling you, and you have to be told, or you have to look it up, the density of the oil is 50 pounds per cubic feet. 50 pounds per cubic foot. That's the density. Okay. And we want to remove the water from the very, very top. Okay, we want to remove the water from the very top. And there's no height to it, okay? There's no height to it. That is, you know, the water is really coming out right from the top. Okay? I can't draw two lines like that. But it's coming out right from the top. So even though it looks like my sprocket is going from above, it's coming from the top. Alright, and I'll tell you that the radius of the sphere is 8. The radius of the sphere is 8 feet. And again, we only want to bring the bottom water, the bottom from halfway down. Okay. So, we know that the work is going to be the integral of the volume times the density times the distance times dy. And you know, if y goes up and down, we know that halfway is 8. So the water that we're going to bring is from 0 to 8. We're going to bring down the bottom circle, and then the circle right above that, and then the circle right above that, and the circle right above that circle of water. So the volume is going to be pi r squared times delta y. Which makes me want to think about something that I've been saying. You know, volume and the dy, they're going together. Maybe I shouldn't have dy here. Oops. I shouldn't have dy here. The volume, sorry about that. Oops. The volume is pi r squared dy. That is the volume. So we did them right. I just failed that I wrote it down wrong. Okay. This here is the area. Pi r squared is an area times the thickness. That gave us the volume. Okay, so right above, I'm going to cross that out. That's the formula. I apologize. Now, you can change it a little bit. You can call V, replace it with A times the density times the distance, and when you multiply A by dy, A times dy is the volume. Okay, but I prefer to say volume. And again, I shouldn't be saying dy. Dy comes from the volume. Okay, so let's erase the dy. As I said, the volume is pi r squared times dy. But r is 8. Why is r always 8? So it's pi times 8 squared. Okay. And that's always nice because it's just a constant. Times the density. And the density was given as 50. And notice that the density is in feet and the radius is also in feet. So the units are fine. Now, we need to figure out the distance, and for the volume is going to be pi r squared times dy. And y is going to go from 0 to 8. Now, what is the distance? That's the key thing that we need to figure out right now. What is the distance? Okay, so we have the density. I'm just moving it down. Okay, so now the distance. If you take this circle right here with thickness, so that circle is at some y value. It's at some y value. The question is, how high do you have to lift it? And we also have another problem, but we'll talk about that. How high do you have to lift it? Well, if this is where, if that's their x-axis, so x is 0 here, and the radius is 8, that means the diameter is 16, you have to lift it 16 minus y. It's the top minus the bottom. If this height is y, if that's y, well then the remaining height must be 16 minus y. Okay. Now we have a problem with the area. I really blew that. I apologize. Okay, it's still going to be the area times dy. But what is the area of this circle? It's not pi times 8 squared. I mean, it is pi times r squared. But what's r? You know, this radius right here is not as big as that radius, which is not as big as that radius. The radius at the very beginning is 0. And then at some point in the middle, it'll become 8. And then it'll start getting smaller and smaller and smaller again. So we need to find out what the radius is for any given height. Well, this is a sphere whose equation is, well, you know, if we just think of a circle, and we know, you know, here's this circle cut in half. And actually, there's the y-axis. If we knew that this, just half, was 2 feet, well then, okay, I got it. Every cross-sectional area is a circle. Every cross-sectional area that we're going to bring up is a circle. We need to know the equation of that circle. We need to know the equation of the circle. Now, if you just have a circle of radius 8, that means x squared plus y squared is equal to 8 squared. That means y squared is 64 minus x squared. That means that y is plus or minus the square root of 64 minus x squared. Okay, let's just keep the top half. Okay, now you have this circle. And that's the center, believe it or not. I want to know how long that distance is given a y value. Well, maybe I shouldn't have solved for y. Maybe I should have solved for x. Given a y, that's the radius. That is what it is. Now, let us be really sure that we're going to plug in the right thing. So basically, we have this right now, and that's the best we have. We have the work is equal to pi times r squared times 50 times 16 minus y times dy, and y is going from 0 to 8. Now, if y is 0, well then, this will give me the square root of 64, which is 8. And you know what? When y is 0, well, how about we put their x-axis there? If y is 0, then that is the radius of the circle. Now, let's just call that the positive y-axis. If y gets bigger, if y is 4 now, if this distance is 4, you'll have that, you'll have that x is 64 minus 4 squared. It's a little bit smaller. I think that's 48. You'd have the square root of 48, or 4 square root of 3. It's a little bit less than 8. Now, what happens when y is 8? That's when you're down here. And it turns out that if y is 8, x is going to be 64 minus 8 squared, which is 0. Square root of 0 is 0. That is working fine. 64 minus y squared square root. Now, we changed the axes, so we need to be more careful about the distance. What is the distance? Now, when you're at, when you're at 0, okay? When you're at 0, you have to lift the water 8, because that is 8. Because I changed the origin. You're going to have to lift it up to 8. Okay? Well, let's see. Shouldn't the distance be 8 plus y? Because I drew on this so much. Let's get rid of it. Okay. We're now putting the origin in the middle of the sphere. This is positive 8, and that's negative 8, and I guess that's 8 as well, and negative 8. So now, if you want to lift, well, let's take an arbitrary piece. So this is 0 for y, so that's y. How high do you have to lift it? Well, it's always the larger number minus the smaller number. You're going to lift it up to here. You're going to lift it y plus 8. If you don't believe that, first you lift it y units. I don't care if that's negative 8 or not. This distance is 8. Distance is never negative. You go y, and then you go 8. Oh, you went y plus 8 or x plus y, 8 plus y, or y plus 8. Now, let's make sure this is working. If you're over here, that's when y is 0. And 0 plus 8 is 8. Yeah. I want to lift this all the way up, 8 feet. Okay, so y plus 8 is the distance. Y plus 8. Okay, finally, we get to move away from figuring stuff out and just getting their integral. So I can factor out 50 times pi. And then when you square that, you get 64 minus y squared, and then you multiply it by y plus 8 dy. I was afraid that was going to be not very friendly, but just distribute. Get 64y plus 480, you get 512 there. 512 minus y cubed minus 8y cubed and dy. Now this integral is straightforward, and y goes from 0 to 8. Now when you integrate, you'll get the integral of that is 32y squared plus 512y. And I just want to check one thing. When you multiply these two, you should get 8y squared. So minus that integral is y to the 4 over 4. And this is 8y cubed over 3. And we go from 0 to 8. Now, you know me by now. I don't like multiplying. So we get 50 times, you know what? That's 4 times 8. Times another 8 squared. 256. That's actually a lot of 8s. I mean 512, but maybe you don't know that. Times 8. Minus 8 to the 4th over 4. Well, you know what? You have 8 cubed from here. You have 8 cubed, and then another 8 from here. But that 8's being divided by 4. That gives you 2. And here, you have 8 to the 4th over 3. Okay. So, 5, 12, 2, 4, 8, 16, 32, 64, 128, 256, 512, 2, 4, 8, 16, 32, 64, 128. So this is 3, 6, 9. Well, you know what? So what am I doing? Okay, so it's 500, that's 512. It's 8 times another 8 times another 8. It's 8 cubed. Okay, so this is going to be 8 to the 4th. So now I can clearly factor out 8 cubed. In here, I pull out 8 cubed, I have 4 left. Plus, in here, I pulled out 8 cubed, I just have 8 left. Over here, I pulled out the 8 cubed, so I have 2 left. Over here, I have one more 8 left over 3. So it's 50 times 8 cubed times 12 minus 2 is what? 10? 10 minus 8 thirds. Well, 10 is 30 thirds. Take away 8 thirds. Be left with 22 thirds. Okay, so the answer is 50 times 8 cubed times 22 over 3. You can multiply that out. And notice, I'm stuck with doing, without a calculator, I'm stuck with doing 8 times 8 times 8. But I never did 8 to the 4th. And I never did 8 cubed here, and 8 to the 4th here, and 8 cubed here, and 8 to the 4th here. And add those numbers. Look, folks, I added 4 and 8, and 12, and 8 thirds. You're going to be adding thousands here. You're going to be adding thousands. I added single-digit numbers, and then I took away a fairly small fraction. Don't multiply out so quickly. Alright. Now, there's another type of work problems that you're going to see in this course, and it's called Hooke's Law. Now, before we talk about Hooke's Law, let's just talk about springs for a little bit. Suppose you have this little spring, maybe you got it out of your pen, versus this really heavy duty spring. Okay, and I want them to be the same height. Possibly if you put a penny on this one, it would compress. You're going to have to do a lot more to compress that spring. That kind of motivates something called a spring constant. Every spring has a constant. It says how stiff it is. This spring will have a very small spring constant. Because, if you just put the weight of your pinky on it, it would compress. You're going to have to put hundreds and hundreds of pounds on that spring to compress. The same amount as the less spring did with the weight of your pinky. That's one thing. Another thing is, if you take this spring, whether it's the small one or the big one, good luck doing it with the big one. But you've done this before, I bet. If you really push down heavy enough on that spring, guess what? It's no longer a spring. Okay? It's no longer a spring. If you don't believe it, take the spring out of your pen, push it down. And take a very long spring. It has to be long, not from your pen, but the diameter of what's in your pen. Okay, you take a very long, thin spring, you push it down. I mean, basically what's going to happen is when you push it down, it's going to start going like that. It's no longer a spring. So when we talk about a spring constant being whatever, it's only valid if it's still a spring. You can take this spring and pull it up. And if you pull it up, if you pull it up long enough, it'll just become a straight wire. Okay, same with this one. Same with this one. Again, good luck doing it, but if you had the right equipment, you hold down this piece, you cement it into the ground, and then you take some real heavy duty equipment and you pull it up. Okay, and as long as the spring doesn't break, it will become just a line, and it's no longer a spring anymore. So whenever we talk about Hooke's law, it's only valid if you really have a spring. Okay, if you compress it enough, it can deform. If you pull it apart enough, it could deform. Now, when it comes to Hooke's law, the formula is that the work is the force times the distance. Which means this. If you have a spring on a table, okay, and now the force is K times X, or K times Y, times the distance. Okay, Kx is the force of the spring, and K is the spring constant. So, how much force, what should F equal if you want to compress this spring so it is now like this, not below, okay? That is, you pushed it in that amount. It's really up here, okay? So, you pushed it in that amount. That is what X is, how much you pushed it. Same thing if you try to pull it that same amount. Maybe now it goes out to there. Okay, it's going to be the distance times how much you moved it times the spring constant. Of course, it has to be a function of the stiffness of the spring. Again, you take this really little spring, and I say move it that amount, and you just go and you push it with your finger, and it moves in that amount. And you did some work. It was easy work, but you did some work. So now I give you this big spring. Hopefully I drew it the same length, okay? Let's make believe it's the same length. But then I say move it in the same amount. It's not going to be easy. For this one, maybe you put your palm of your hand here, and then your other hand or finger you pushed on it. Over here, you're going to have to put it against the cement wall and hope the wall doesn't lose and cave in. And then, maybe you back your car up to here and you back up. And then maybe you'll move it that amount. It's not going to be easy. Okay, enough of that. This isn't a physics class. So now, Hooke's law, now what I wrote is when it's discrete. But if you're going to move it along or a constant distance, it is just going to be the integral of kx dx. A force of 750 pounds compresses a spring 3 feet from its natural position. The natural position means where no force is acting on it. The spring is hanging out. There's no load on it. Doesn't have a car on it. It doesn't have your hand pushing on it. It's just in its natural state. So we want to find the work required to move the spring an additional 3 feet. So basically, it's going to be the integral, W is equal to the integral from 3 feet to 6 feet of kx dx. Well, this is going to be kx squared over 2 from 3 to 6. So the k over 2 we can factor out. When you put in the 6, you get 36. When you put the 3 in, you get 9. 36 minus 9 is 27k over 2. But we want to know what k is. So we found the answer up to k. But they gave us some information. They told us a force of 75 pounds is required to move this object 3 feet. To move their spring, compress it 3 feet. Well, we know that F is equal to K times X. Well, the force is 750. K we don't know, but X is 3 feet. Well, 250 times 3 is 750. Because 25 times 3 is 75, add a 0. This implies that K is 250. So this work is equal to 27 times K, 250, over 2. And 2 goes into 250 125 times. And 27 times 100 is 2700 plus 27 times 25. How much is that? That's going to be 675. And when you add these, you get 3375. And that would be the answer to that problem. Now, let us try another one like this. Suppose a force of 60 pounds stretches a spring 1 foot. Okay, so how much work is done to stretch the spring 6 inches? How much work is done to stretch the spring 6 inches? Well, this is in pounds, this is in foot. We get foot pounds. But what is this inches all about? It's just a half a foot. That's how we should think about it. So again, the work is equal to the integral of kx dx, and x is going from 0 to a half. So we get kx squared over 2 from 0 to 2. I can factor out the k over 2, and I evaluate x squared from 0 to 2. So that's going to be, the evaluation is going to be 4. So I get 2k. But what is that? Now, they told us now, that's the best we can do unless they gave us some other information which might help us find out what the spring constant is. And they told us that a force of 60 pounds will stretch the spring 1 foot. Now, we know that force is K times X. That's Hooke's law. And the force was 60 pounds and it moved 1 foot. Dividing, K is 60 pounds over 1 foot, or just 60. K is 60. So it's 2 times 60, or 120. The work is 120 units of work. And that completes this section on work.